You are welcome to Jonathan online class. Here in this class, we have practical analysis on the board. Of course, this is physics, precisely electricity. Yes, last time we looked into the practical analysis of the current SSTE and mechanics. So this one now is centered on electricity. Of course, you know in the SSCE, both WAEC and NECO, NAPTEL, that they test the students with the knowledge of practical application and analysis of mechanics and in the area of optics and as well electricity, and sometimes thermal physics with other areas, as the case may be. Now, in this case, given this circuit setup or with the equipment or materials, you'll be able to make a circuit connection which will lead to determination of certain variables in the circuit. Of course, we have our battery. This battery here should be about 3 volts. That is 1.5 volts by 2 of the dry cell. Then here we have the key or the switch. We have this one is the resistance box. This is the resistance box. And resistance box containing different resistors. That is resistors of different values or resistance of different values. You can have 1 ohm, 2 ohm, 3 ohm, 5 ohm, and so on, 10 ohm, 20 ohm, depending. It might be switch type, it might be the box type, which has plugs. Of course, you know when you plug off, you are making use of the resistance there within. Okay, then we have here the ammeter. The ammeter here is for reading. This is the ammeter. The ammeter. This ammeter is for reading the value of currents flowing in the circuit. Then we have the bulb or lamp. This is the bulb or lamp. Of course, the bulb or lamp has its own filament inside, which will constitute resistance to the circuit. Good. Then we have here the rheostat. The rheostat, which is a variable resistor with which we can adjust the value of the current flowing in the circuit. That is the rheostat. Okay, now look at the first. There are two connections here. The first one is the series connection. That is a connection in which all these components are connected in one line, that is in series. Do not forget that these lines here represent the wires. These lines represent the wires. And each of these components has two ends or two connecting points or terminals, which leads to positive or negative terminal that is being determined by the battery terminals. Okay, after your connection, you check continuity flow. Make sure there's tight connection. Of course, one of the precautions. In the continuity flow, if there's backward flow or anti-clockwise flow in your ammeter or in voltmeter, if you have a voltmeter, in a case that involves voltmeter, what you need to do, you change the terminal of your cell to get your right clockwise continuity flow. Okay, then this is our circuit. So the first circuit here is the series connection to determine the value of I, the current flowing in the circuit, which I call I1. The essence of this experiment analysis or practical analysis is to know what happens when all these are connected in series, when the lamp is connected in series with the resistor. What happens as we are changing the values of the resistors using the resistance bus, having determined the maximum current flowing in the circuit. Some people might be wondering what the essence of the rheostat. The rheostat here is first after connection, you close the key. This is the connecting circuit, something like this. After the connection, you close the circuit. Remember, this is my positive terminal, this is my negative terminal. It can be reversed depending on the circuit diagram. So after the connection, then you close the key or the switch. When you close the key, then you check the circuit flow, the current flow. Then the essence of this is to know what happens to this bulb or lamp when it is connected in series with this resistor. Then, and again, in the set of 2 or connection 2 will be in parallel to determine what happens to the lamp or bulb when it is connected in parallel with the resistor. That is the resistance bus. Here you have the resistors. As you are varying the resistors, what will happen to the lamp? That is the brightness of the bulb should be observed as well. The brightness of the bulb should be observed in both cases, in both connections. That is series connection and parallel connection. Of course, we know that when we connect resistors in series, the same current flows. When we connect resistors in parallel, there is current divide depending on the connection. Okay, now here we have current divided with the same potential difference across the what? Parallel connection. But in series, we have the same current flow with what? A different potential difference divide. Okay, now in this case, now having connected this, the first task here is to close the key. When you close the key, you adjust the rheostat. The rheostat has connecting point, the top and bottom. That's why I draw it this way. This one stands for the top connection point to the conductor. Here is the bottom connection point to the conductor out. So you adjust it with it has a device for adjusting it. You flip the device, you adjust it. When you adjust it to the point, and you are observing the current. As you adjust it, you'll be observing the current deflection. The current deflection. So when the current deflects to the maximum point, then you know it has reached to the maximum point by adjusting the rheostat to the minimum. Then when you do that, you now record your maximum current in the circuit in the series connection, having adjusted with the word rheostat when the key is closed. And this resistance bus, the resistors will be intact. You will not make use of any. That is when the resistance bus is what? At zero value of what? Resistance. By implication, you have not unplugged any if you are using the plug type, or by switch type, it is at 0 point. You have not switched it to 1 or 2, any value. The switch type looks like that of the fan, the switch of a fan, which has 1, 2, 3 regulator. Good. So at that point, you now determine the highest value of the current. Look at your ammeter. You record the highest value of the current as I take it to be my I alpha. That is in series. The maximum current flowing in the circuit, when by adjusting the rheostat, I recorded it as what? I alpha. Then my I alpha now, I don't want to keep figures here, but this is the analysis, a guide, interpretation. You can obtain, when you follow this procedure and analysis, you can obtain values which can vary with other person's experiment, depending on the apparatus, the wires used, the resistance, and the devices. Okay, so of course, you know, in exams, students are not expected to have a uniform thing because it depends on several factors on the components of the circuit. But the important thing is that the same observation should be made in the terms of the principle guiding it. If it is in line with Ohm's law, the same observation will be made. If the trend is increasing in the variables, it should be increasing all through. If the trend is decreasing, it should be decreasing all through. That is where the judgment is based in marking the SSCE exams and every other experimental analysis examination or test. So here, you see I alpha. My I alpha, I use X 0.00 ampere. The unit of current is ampere. That's my I alpha. That's the value obtained when this is adjusted at the maximum current obtained here in the ammeter, I alpha, before the procedure, before adjusting, varying the resistors values in the resistance bus as given in the question. Like I use here, I take for instance, I have these resistors values to be varied in the resistance bus. So that's for the series connection. Then, of course, the EMF of the cell, like I said before, is 3.0 volt. I recorded it. That is 2 dry cells for the experiment. Then, if you are asked to record the terminal PD when you close the circuit, you can also record your terminal word PD when you connect the circuit, which is expected to be a bit less than the EMF of the cell. We can call the terminal PD V0. The V0 may be about something like, maybe you can have something like 2.80 volt, for example, which is a bit less than, or 2.50 volt, depending. But we are not expected to do this because in this case, we are not using any voltmeter here. So there is no voltmeter here. So we are not, you might not be expected to record a terminal PD. Okay. Now you continue. Then for the series first, then you see what you observe. As you do this, when you get the maximum current, the brightness of this bulb will be very high. It will be very high. As you are adjusting it, you'll be looking at the bulb and this, it will be increasing the brightness the glowing or the shine of the bulb will be increasing. It will increase to maximum. Then, when that is done, you start the procedure. You remove, for example, 1, depending on what you are instructed to vary in the values of the resistors or resistances. Let me say, for example, to remove 1 ohm, you unplug 1 ohm or switch to 1 ohm if you are using the switch type regulator, resistant bulbs. 1 ohm. When you unplug 1 ohm, if you are using the plug type, you are using 1 ohm, then you record your value here. The value of I1, which what I call I1, that the I in series. That is when the current is in series. Then this is my parallel. In parallel. That is it. You record your I1. Then you also now you check the current. When you remove 2 ohms. 2 ohms, you also determine the value of your what? Your current flowing. So you will notice that as you are doing this, what do you think will be happening? Remember our Ohm's law, that V is proportional to what? I, so that V is equal to IR. So in line with this Ohm's law, you will now observe that when you are, and this is series connection, as you remove 1 ohm, this maximum current I alpha will begin to drop, to be decreasing, because you are now increasing the resistance. Before, the resistance bus was at 0. Now you are increasing the resistance. The current value will be decreasing, and the brightness of the bulb will be reducing. Take this, note this point. As you get to the maximum point initially, at the maximum, this will be bright, the brightness will be to the maximum. But as you are increasing the resistances, the brightness of the bulb will be decreasing, while the ammeter reading value will be also decreasing. So as you are increasing the resistance, then this will be decreasing. Because from this equation, you can notice that if V is equal to IR, therefore I is equal to V over R, which by implication I is inverse to R. So the current flowing in the circuit is inverse proportional to the resistance in the circuit. So the higher the resistance, the lower the what? Current flowing in the circuit. So as we are increasing the resistance, the current is decreasing. So here will be decreasing value. The values here will be decreasing. You have decreasing values here. So that is what you observe here. There will be decreasing values here. Then you come to I2. When you come to I2, so this is what the trend we are going to observe here. Decreasing values of I1 decreasing. Here your I1 should be decreasing all through. I1 decreasing. But get the point. You should know that the first I1 you get here will be less than this X. That the value this X represents. That's I maximum when the resistance is 0. So it will be dropping. The first one here will be less than this, and the second one will be less than the other one, will be decreasing down as we are increasing the resistance. Very important. Then the brightness of the bulb will be reducing. The bulb will be decreasing, dimming, because you are increasing the resistance and the heating of the what? The wire. That is it. Okay. Then we now go to, after this, you'll be expected now to repeat the same experiment, and you'll be instructed to connect in the second phase now. Now take out this resistance bus and connect it in parallel to the what? Bulb or lamp. Other things being there, remove the resistance bus, connect it in parallel to the bulb, and observe what happens when it is in parallel to the lamp or bulb. Then you also adjust this rheostat. You adjust the rheostat as well. Adjust it to get the maximum current when it is connected in parallel here now. You adjust. When you adjust it, let's take our maximum current in parallel adjustment of the rheostat for maximum current reading of the ammeter when the key is closed and the resistance bus is at 0. Let's take it to the what? I beta. I call it I beta to differentiate the two quantities. I beta. Then, of course, I is the symbol for current conventionally. I beta. Now I take the maximum value to be Y.00 ampere. Y.00 ampere. So at the maximum current in parallel, I have Y.00 ampere. Now note significantly and very important. You should know that your I alpha should be greater than what? I beta. The I alpha should be greater than I beta. That the current, the maximum current in the series connection should be greater than the maximum, that your I alpha is less than I beta. Pardon? I alpha is less than I beta. That is, the maximum current value when collected in series should be less than the maximum current value when collected in what? Parallel. I mean the resistance bus connection. Or conversely, you can say that the I beta is greater than what? I alpha. That is, the maximum current value when the resistance bus is connected in series, in parallel to the lamp or bulb, the maximum current value reading of the ammeter is greater than the maximum current value reading of the what? Ammeter when connected in series to the what? Lamp. That is what this symbol represents. I alpha should be less than what? I beta. There's a reason for that. Very simple. In series connection, the same current flows and the value of resistance increases. Of course, you know, in series connection, you have the maximum value of resistance values when you have resistors in series. Remember, it is addition of R1, R2, R1 plus R2 plus R3 plus R4 continuously. But in parallel connection, when you want to get resistance, the net resistance or equivalent or resultant resistance in parallel, it is the reciprocal. And at the end of evaluation of reciprocal or the value, you get a minimum value. So the value of resistance diminishes when connected in what? Parallel. For that reason, since it is diminishes, the current value here will be high because the effective resistance here will be less than this one in series. So there's more effective resistance in series, resulting to a lower flow of current. This one, there's less effectiveness of resistance, resulting to high flow of current. So the brightness of the bulb will be greater here when maximum than the first connection. It will be greater in parallel connection, the brightness of the bulb, than in what? In series connection. So you should be mindful of this. Okay, so that is what is observed, because you might be asked to explain this. What happens in the brightness and the why. I've just explained that. Okay, so you have your I beta, which I take to be Y.00 ampere. You continue the same procedure. So the same thing will be observed as you are increasing the resistance value here, 1 ohm, 2 ohm, 3 ohm, as the case might be. You also observe that as you are increasing the resistance, in whichever case, the current will be what? Reducing. So the value of the current you are going to obtain here will be less than the I beta in the parallel, the value. But there's something important. The value here, I2, will be decreasing as well. Decreasing. But there's something important. There's something you should know, that the values in this column should be greater than the values here, because there is more current flow here than in what? In series. There's more current flow in this parallel than what? In series. So brightness of current here will be greater than this one. That's what you should know, because there's less effectiveness of resistance in circuit 2 than in circuit 1. For instance, if I have here to be 0.6, for example, then here will be about 0.8 or 0.9. That's what I mean. Assuming that I have 0.60 ampere here, here will be about 0.8 or 0.9 ampere, for example. Good. Of course, what is here should be less than what is here. What is here should be less than what is here. So that is what you are going to observe. So you should know that I1 is less than I2 in this column. I stated it here. I1 should be less than I2. In other words, I2 column values is greater than what? I1 column values in each case of the resistance variation. Good. When you do that now, you'll be expected to evaluate, I call it gamma, a quantity. Evaluate gamma equals to I1 times I2. That's the product of I1 and what? I2. I1 times I2. You multiply them. I1 times, as far as the unit should be ampere square. So I1 times I2, I1 times I2, you multiply them and get ampere square. Good. When you multiply them, you write your values. The values will be written here. These are the values obtained. Some question may ask you to add and divide and get average. You might be asked to add I1 plus I2 and get the average, and the quantity will be called, it could be called theta, K, gamma, or any symbol. So, but in my case here, I predicted and I used the analysis of I1 times I2, which is the product, and I get A square, which is the unit of what? Current in product. Then I have here now, of course, I1 times I2 is like saying I squared. Do not forget. It's like saying I squared. Of course, the unit will now be ampere square. I have a reason for that of data evaluation, which because every experiment targeted to obtaining a certain quantity or constant in the circuit, which is in tandem with a given principle or law verified. Now here is R inverse, that the inverse values of these resistances. R inverse. You evaluate this with your calculator. Evaluate this with your calculator. Of course, you know, since this is decreasing, this will also be decreasing. Because it is product of these two. Then for this value, because this one is increasing, the resistance is increasing, the inverse value should also be what? Decreasing. When you have an increasing value, the inverse reciprocal should be decreasing. So here would also decreasing. So this is like opposite case of what we observed when we treated our mechanics, our Hooke's law, simple harmonic motion in mechanics, number 1 question of the SSE exam. So we observed that the columns were increasing. In this case of electricity, you observe that the columns are what? Decreasing. So they're like opposite. This will help you to remind. It will help you and give you a guide to remind you when you are doing your analysis or candidates as we are preparing for the examination, like the NECO examination that is around the corner. Okay. Then now having this now, I think I've given enough explanation. Then the thing again is to plot a graph. You might be asked to plot a graph here. The likely graph here is to plot a graph of gamma, what I call gamma here, that is product of I1 and I2. Graph of gamma against R inverse. Plot a graph of gamma against R inverse. Of course, you know, if you are plotting this column against this column, both of them are decreasing. Since both quantities are decreasing, you are going to get a positive graph. A positive graph goes like this. A positive graph goes like this. You're going to get a positive graph. That is it. Graph of gamma against R inverse. So it goes like this. So you get a positive graph and you get your slope. So in getting your slope, you get your slope quantity value, get your intercept on gamma axis. That is my vertical axis. Get the intercept there and record. Then you might be asked to make an evaluation, or you might be asked again to find what the slope represents. Of course, in this case, mathematically or analytically, in physical quantity of electricity, the slope here, if you plot gamma, that is I square, against R inverse, it will represent power. So the slope of this graph I stated here will represent the power in the circuit. Do not forget that power is equal to, is given as, why did I say power? Power is given as I square R as one of its relations. Of course, we have IV as well. So the power is given as I square R. So if I have plotted graph of I square against R inverse, that should be I square over 1 times R over 1, which is I square times R. That is I square R, which will give you power in watts. So that is the secret there. You determine the power in the circuit. That's the power of the rating of the bulb, perhaps. The lamp in the power in the what? Circuit. Good. Okay. Why is the bulb brighter? Or in which case will the bulb brighter? Another question may be like that. And why? I said it earlier that the bulb will be the brightness of the bulb will be brighter in circuit 2, that is in parallel connection, than in what? In series what? Connection. And the reason is because in series there is more effective resistance in the circuit. In parallel, there is less effective resistance in the circuit. And according to Ohm's law, I is inverse to what? R. Simple. Then precautions taken. What are the likely precautions? Very simple. In every electricity, you ensure tight connection of the circuit to avoid partial constant and ensure continuity flow of current. You ensure tight connection. Should be stated in past tense. Another one is that you avoided error due to what? Parallels when taking reading on the ammeter, or you took note of 0 error before taking reading on the what? Ammeter. Is a precaution there. It's acceptable precaution. Another one is that you remove the key when reading is not being taken to avoid what? Draining the what? This battery, or running down the what? The battery, or to save the battery life. So you remove the key when reading is not being taken. Is another precaution for this electricity. So I believe with this analysis, you have understood the principle and the procedure in this practical experiment number 2, electricity, for the ongoing SSCE exam. For more of this, you reach out to me through my contact number, and for your question and more of physics and mathematics tutorials, including practical analysis, through my WhatsApp contact or call. You can also subscribe to my YouTube channel to be notified